Hi, today we will discuss magnetism in matter. We have seen magnetic materials like iron, cobalt, nickel getting attracted by a magnet. Though magnetism is universal, it is present in tiny atoms as well as it is present in vast universe. It is present in galaxies. Magnetism is also present in living creatures, in all the birds, in beasts, and in human being too. This magnetism is known to mankind from time 600 BC. There was a place, Magnesia, in Asia Minor. Today we call this place Turkey. And there we had magical stones. When shepherds used to go to those stones, their shoes stuck to those magical stones. Their shoes, because of they had iron nails in them, and since it was in Magnesia, it is called the naturally attracting stones are called magnet. Magnet has a directive property. When you suspend a magnet freely, it always comes to rest in north-south direction. This property was known to Chinese from time 400 BC, and this property was used in navigation also. So let us list some of the properties of magnet. Our earth is a magnet and its direction is from south towards north pole at an angle 11.3 degree from north to west at present, and this direction of magnetism changes with time. In past 10,000 years, there is several even reversals of this magnetic field. A magnet has attractive property. Like poles repel each other and unlike poles attract each other. You have directive property of magnet. A magnet always is directed from north-south direction. Then you cannot separate the poles of a magnet. These are some properties I have listed. Now, next thing, the origin of magnetism. The origin of magnetism is circulating charges. In 1864, work of Ampere and Maxwell suggests that it is due to motion of charges. Now, magnet applies force from some distance. It is a non-contact kind of force. It creates some field and the field applies force on magnetic material. This field can be well understood with the help of field lines. So, what is magnetic field lines? Let us discuss. Here you have a magnet in diagram and some iron filings. Are sprinkled on this magnet, and under the influence of two forces, gravitational force and magnetic force, the iron filings arrange themselves in a particular pattern. You can see it is forming circular loops, closed continuous loops, where the closed continuous loops are formed. These continuous lines are called magnetic field lines. Here, these magnetic field lines can be understood with the help of a magnetic compass needle. So, when you place magnetic compass needle at different locations in the vicinity of a magnet, then you will find that the red pointed end of this compass needle is directing along a particular direction when it is close to any bar magnet. And this is the direction of magnetic field. So in this diagram, the direction of magnetic field is from this red end of the magnet, which is called North Pole. This is your North Pole, and the black ended part is called South Pole. This is your South Pole. Magnetic field lines are away from North Pole, and they are making closed continuous loop as it emanates from North Pole and it goes to South Pole externally, and then it continues inside a magnet, forming a closed continuous loop. The same is happen on the other side also. So the properties of what is your magnetic field lines, let us discuss. Field lines are closed continuous curves. The relative density of field lines says about magnetic field at any place. And the direction, tangent direction on these magnetic field lines. This is your tangent direction away from North Pole, gives you the direction of magnetic field at that very point. So, the tangent on the magnetic field lines away from North Pole of a magnet gives the direction of magnetic field at that point. Your magnetic field is a vector quantity, so it has magnitude and it has direction, and both are given by magnetic field lines. It gives the magnitude of magnetic field by relative densities of the field lines. Here you can see that in unit area the density of field lines, number of field lines is more, and if you take a unit area at this very place, you can find the number of field line is less. So this relative density suggests that field is stronger near pole, and field is weaker at far places. So relative density gives you the magnitude of magnetic field, and direction is given by the tangent on these magnetic fields away from North Pole. Next, magnetic flux. Magnetic flux is synonymous to magnetic field lines. So this topic, magnetic flux, can be well understood looking this diagram. Here you can see I have taken unit area at two places, at a near place and at a far place. And you will observe that number of field lines, that is flux, is more at near place and it is less at far place. Here we know that field is strong. So if field is strong, then flux also is more. Field lines also are more. So we can say that flux is proportional to magnetic field B. Now, if you take a large area, then you will observe that more number of field lines are passing through this area. So if area is large, field lines also becomes large. It means flux is directly proportional to area. Now let us consider a third condition, that if this area that I have taken perpendicular to field lines, let me take the area parallel to the field lines. Now you can see that no field line is passing through this area when field area is parallel to this magnetic field line. Now if you take area vector, then you will find that in this situation angle between area vector and field line vector is 90 degree. So when angle between area vector and field lines is 90 degree, net flux through the area is 0. And we know that cos 90 only is 0. So the flux also is proportional to cos theta. It means flux also depends on orientation of magnetic field and area vector. Now when you combine the three, you will find that magnetic flux is proportional to B, proportional to A, and it is proportional to cos theta. When you combine the three, you will find that flux is equal to BA cos theta, and this is actually dot product of vector B and A. So this is your flux. Flux is your number of field lines passing through any given area, and it is a scalar product of magnetic field and area. Its SI unit is, it is a physical quantity which is scalar one. Flux is a scalar quantity as it is dot product of two vector quantity, and its SI unit is Weber. You can also write for SI unit, for B you can write Tesla multiplied by for area meter square. So these are the SI units of magnetic flux. Now we have Gauss's theorem of magnetism. Gauss's theorem says that flux through any enclosed surface any enclosed surface is 0. That is, integration of all the magnetic fields along an enclosed surface is 0. That is flux phi, which is equal to surface integral of B dot ds. This is equal to 0. Let us see this in diagram to convince with Gauss's theorem of magnetism. Here we have a bar magnet, and bar magnet along north pole I have taken a closed surface, and you can inspect that number of field lines entering this enclosed surface is same as the number of field lines emanating from the enclosed surface. So net number of field lines becomes equal to 0, as total number of field lines entering is equal to total field lines emanating. So their sum becomes equal to 0, and field lines are called actually flux. So flux becomes 0. This suggests that if you integrate all the magnetic field along a closed surface, then sum of the magnetic field along closed surface must magnetic field of a bar magnet realizing magnetic field of a solenoid. Here you have a solenoid having length 2L and at a distance r from origin of solenoid at a point P. We are interested to find magnetic field B. Here we are to find magnetic field B. The radius of the solenoid given is A. Now I take a small thickness of this solenoid, dx thickness, which is at a distance x from the origin. And firstly, the scheme is that firstly we will be finding magnetic field due to this small thickness at point P, and then we integrate the magnetic field due to all such small thicknesses in this solenoid. So this is the working scheme. We know that magnetic field due to a circular loop is given by B is equal to mu naught upon 4 pi 2 pi I current flowing through the circular loop into square of radius of circular loop divided by radius square plus distance square whole power 3 by 2 along the axis. So this is magnetic field by a circular loop. If we take this field to be, let field of the thickness is dB. Total number of turns of the solenoid is capital N. Therefore, total number of turns per unit length will be equal to number of turns capital N per unit length, and here the length of solenoid is 2L. And if this is n, so n is equal to this much. Now, if the current in one turn of the solenoid is equal to I, then total current in thickness dx will be equal to current in one coil and the number of coils in that thickness. So number of turns in unit length is n, therefore number of turns in dx thickness is n dx. So this is total current flowing. Now I'll put all these values, current flowing and everything, in this equation. So therefore dB is equal to mu naught upon 4 pi 2 pi and then I is your this value, I and dx into r square. R is your a, so a square, radius is a, upon a square plus and this distance from small thickness dx to point P, where we are to find magnetic field B, is r minus x. R is your distance from origin, this r minus this x. Okay. So this is your r minus x square whole 3 upon 2. So this is the magnetic field due to small thickness. And to find total magnetic field at point P due to whole solenoid, we need to integrate this equation. So total magnetic field at point P due to whole solenoid can be obtained by integrating equation 1 under proper limit. Therefore, integration of dB is equal to integration under limit. Here your whole length is from minus L, here origin it is at 0 length, so minus L to plus L. So limit should be from minus L to plus L, and this is your mu naught upon 4 pi 2 pi n I dx a square upon a square plus r minus x square whole 3 by 2. Now this integration process is little bit elaborate, so we will do in a short process. We will assume that this radius and this distance x is very smaller than distance r. Then the equation is simplified. So this dB, integration of dB is b, and this is equal to, let me take all the constants outside the integral sign. Constant cannot be integrated. Mu naught upon 4 pi 2 pi n I a square divided by, here I have neglected a and x, so r square power 3 by 2, and 2 will be cancelled, so here rest thing is r cube, and then integration of dx only from minus L to plus L. Therefore b is equal to mu naught upon 4 pi 2 pi n I a square upon r cube, and dx is your x, integration of dx is x from limit minus L to plus L. Here pi a square, this term, this is actually area of that circular small thickness. So I'll replace it with area. Therefore b becomes equal to mu naught upon 4 pi 2 n I a upon r cube L minus L. So you get b is equal to, I am writing magnitude only here at every place. So this becomes equal to mu naught upon 4 pi 2 n I a into 2L divided by r cube. Now this 2L is your length, and here n is number of turns per unit length. So number of turns per unit length into total length, this is your total number of turns. So this becomes equal to mu naught upon 4 pi 2 capital N total number of turns I into A, and this is your total current, total number of turns into current in one turn upon R cube. Therefore magnitude of B is equal to mu naught upon 4 pi 2, and this current into area, this is called magnetic dipole moment. So this is the magnetic field of a solenoid, and same is the magnetic field of a bar magnet too. The magnetic field of the solenoid can be considered as magnetic field of a bar magnet. As the field lines are similar. So I conclude